Well, hello there. Let's begin our new unit looking at halogen derivatives, where today's lesson we're going to introduce halogenoalkanes and look at some of their reactions. Lesson objective: investigate substitution and elimination reactions of halogenoalkanes and describe some of their uses and pollution. Learning outcomes we're addressing from the Cambridge curriculum. Halogenoalkanes are exactly what they sound like. They're alkanes that have a halogen. So we've essentially just substituted one of the hydrogens for a halogen, halogenoalkanes. So if one or more hydrogens replaced by halogens, our halogens being our group 7, fluorine, chlorine, bromine, etc. You can have a number of different substitutions on the same molecule. So you can have di-substituted, dichloro, you can have tri-bromo, you can have a chloral and 2 bromos, you can have tetrafluoro, etc., etc. We're predominantly focusing on the mono-substituted halogenoalkanes. So just one of the hydrogens have been replaced with a halogen. So based on that description, we could assume they have a general formula this. If our alkanes have a general formula CnH2n plus 2, but if we're substituting, we're replacing one of the hydrogens for a halogen, then we'll minus one of the hydrogens to have 2n plus 1, and X, where X denotes whatever halogen we have attached to them. They can be classified based on how many carbons the carbon that has the halogen attached to it has also attached to it. What do I mean by that? We have primary halogenoalkanes. The carbon bonded to the halogen has one other alkyl group that is bonded to it. For example, chloropropane. If I draw that, we have, let me do a little title here, primary halogenoalkane, halogenoalkane. So for example, my example is chloropropane, prop having 1, 2, 3, chloro, and I mean we should really say 1 chloropropane, shouldn't we? Because we could have 2 chloropropane. We've got a chlorine on carbon number 1, and then we have all our hydrogens filling in there like so. So when we're classifying them as primary, secondary, or tertiary, we look at the carbon that contains the carbon-halogen bond, and we see how many other carbons are attached to it. This has one other alkyl group, so it is a primary halogenoalkane. Might be able to see where we're going from here. Our secondary halogenoalkanes, the carbon bonded to the halogen has 2 other alkyl groups bonded to it. For example, 2-bromopentane. So if our secondary halogenoalkane, we're going to have, what do we have? Pentane, 1, 2, 3, 4, 5. And we have the bromo on carbon number 2. So we can see here, this will be classified as a secondary halogenoalkane because the carbon that has the halogen carbon bond is attached to 2 other carbons. So we've got 2 other alkyl groups attached to that carbon with the halogen. Therefore, we can classify it as a secondary halogenoalkane. And to follow that in its natural conclusion, we're going to have tertiary halogenoalkanes, where obviously the carbon bonded to the halogen has 3 other alkyl groups bonded to it. For example, 2-chloro-2-methylbutane. So let me come up here and do me tertiary. So what do we have? We got 2-chloro-2-methylbutane. So a butane chain, 3, 4. Yep, plenty of space. We got a chloro on carbon 2. We got a methyl on carbon 2. And then if I fill in all the other hydrogens there, we can see this is going to be a tertiary because our carbon that has the halogen on it has 1, 2, 3 other alkyl groups. So important that we can classify as primary, secondary, or tertiary because, as we will see later on, depending on how we classify them is going to depend on the kinds of products we form in organic reactions, but also the kind of mechanism that we will follow. That the reaction will take place will depend on these classifications. There we go. So the properties of the halogenoalkane will depend on the class, the length of the carbon chain, and the type of halogen that is bonded to it. So let's consider the differences in the electronegativity of the C-halogen bond. This means they can undergo certain reactions. So we know electronegativity is the tendency for the electron pair in a covalent bond to be more closely held by one atom, giving it a partial charge. And that's exactly what we see on our halogenoalkanes. We have our halogens, which are quite electronegative. I mean, fluorine being the most electronegative, chlorine also very electronegative. So we have a partial charge on the halogen, which gives a partial positive delta positive on the carbon. So that's going to happen no matter which type of halogenoalkane it is. That should be delta negative. So what that means is that we have a electrophilic delta positive carbon, and this means that there's some key types of reactions that our halogenoalkanes can undergo, including substitution reactions with nucleophiles and also elimination reactions where we lose something, one thing becomes multiple things. So we're going to look at these, and we'll also look at the uses and pollution of halogenoalkanes. So let's start with our nucleophilic substitution reactions. Our polar carbon-halogen bond gives an electrophilic carbon, like we just saw, delta positive on the carbon, and this is leaving it susceptible to nucleophilic attack. With the partial positive charge, this carbon can act as an electrophile, which means if a nucleophile is coming looking for a nucleus, we could potentially get a substitution reaction occurring with a nucleophile, thus nucleophilic substitution. Here we go. The nucleophile can form a new bond with the electrophilic carbon. Halogen can act as a leaving group and break the bond, have heterolytic fission, and that causes a substitution reaction to occur. Now the mechanism of these are very important, and they're quite intricate. Well, maybe not intricate, but there's a few things we need to be aware when we are discussing the mechanisms. So we're not going to go into that this lesson, rather we will look in depth at the different kinds of mechanisms in the following lesson. This lesson, we're just going to generally walk through what is occurring and different types of these nucleophilic substitution reactions. So in the next one, like I say, we'll look a lot more depth at the mechanisms, the actual intricacies with which these reactions occur. So let's have a look. We got 3 nucleophilic substitution reactions we need to be familiar with. The first, substitution with aqueous hydroxide, so alkali hydroxide, aqueous alkali rather. Substitution with a cyanide in ethanol, and substitution with amine in ethanol. So we've got our 3 nucleophiles here that are all going to attack that delta positive carbon. So substitution with the OH group. This is going to transform our halogenoalkane into an alcohol. So we'll either get a primary, secondary, or tertiary alcohol depending on what kind of halogenoalkane it is. Sodium hydroxide added to a halogenoalkane. We provide nucleophilic OH- ions from the sodium hydroxide. This can attack that electrophilic carbon. So if we have an OH- delta positive carbon, we can have the chlorine or the halogen leave as a leaving group, and we substitute the halogen for the hydroxyl, making it an alcohol. Here we go. Complete this reaction based on what we've just read and what we've just said. If I have chloroethane and I react it with sodium hydroxide, finish that reaction, we form the alcohol, we would end up with this. So the chloroethane becomes ethanol. We're substituting, we're replacing the chlorine for the OH, and then the sodium chloride will form from the sodium ions and the chloride ions. We can also show this just as an ionic equation, which I will draw for us here now. Sometimes it's more useful, especially in the mechanisms, just to show the ionic equation. So we got our H3C and then our CH2Cl, so that's our chloroethane, and then we react that with hydroxide ions and we form the alcohol. Let's just do this, H3C, CH2, OH, and the chloride ions. So delta positive carbon, we're going to get nucleophilic attack from our nucleophile. The chloride's going to leave. We have a substitution. Like I say, the specific mechanisms we will focus on next lesson. Let's just introduce these. Carried out into something called reflux. Reflux is a very useful, very commonly used laboratory technique that allows us to supply lots of energy to a chemical reaction without losing the volatile organic compounds that we are both reacting with and we're potentially forming. Another thing that we'll look at in the next lesson, look at the details of reflux. Substitution with cyanide, potassium cyanide in ethanol. So we can refer to this as an ethanolic solution of potassium cyanide. Heated under reflux, so we provide that energy without losing any product with our halogenoalkane. So we use the ethanol because we want the cyanide to be the nucleophile, and this will prevent any sort of byproducts that might form, say, if we can form a alcohol or something like that if we're in an aqueous solution. So this provides nucleophilic cyanide ions that can attack the electrophile carbon to a given, electrophilic carbon to give a nitrile group. Based on all of that, can you complete this reaction? Pause, write the reaction, write the products, and resume. And no tricks here. We just replace the bromine with the cyanide. Substitution reaction, exactly what it sounds like, to get the butanitrile, and then the bromide has left as a leaving group. So this is an ionic equation. Same way we showed a full equation over here, we could show a full equation for this. So let me write that for us now. So we have our CH3, CH2, our 1-bromopropane that we react with the potassium cyanide, potassium being the salt, potassium being the cation to make the potassium cyanide salt. And this is in the ethanolic solution, very important, so that we get the substitution of the nitrile to get CH3, CH2, CH2, what am I doing here? CN. Our nitrile, remember having that C triple bond N like that. And then we get potassium bromide, like so. Now what you might see here, which is something that is very useful, is the fact that we have extended the carbon chain. We've gone from a prop to a but, which is very useful, especially in chemical industry and chemical synthesis. We can extend that carbon chain, used often in industry. Our final one, substitution with ammonia. Again, ethanolic solution of ammonia as opposed to aqueous. Excess of ammonia dissolved in ethanol, heated under pressure, added to the halogenoalkane. Nucleophilic NH3 ions attack the electrophile carbon to give an amine. Here's the third one. Can you complete this reaction? This time we have our chloroethane with ammonia. What would we form to get the amine? Pause, work it out. Hopefully you wrote this. We would just simply replace the chlorine with an amine to get 1-aminoethane or ethylamine. And then hydrochloric acid, because we would form, when this nitrogen replaces the chlorine, we would have a nitrogen with 4 bonds. That would be an ammonium ion. So then we get deprotonation from the chloride to get the amine. Initial substitution will form the primary amine, but then this amine can act as a nucleophile itself if the ammonia is not in excess. So this amine that we form, well, this has a lone pair of electrons there, so that could also act as a nucleophile. So we could potentially form secondary and tertiary amines from this reaction. So this is why we want to have an excess of ammonia, because often we don't want to get a whole mixture of products. We just want to get the one product that we're after, the primary amine in this instance. Excellent. So there were our substitution reactions. Just to say one more time, we'll be looking in depth at the different kinds of mechanisms they can undergo in the next lesson. Let's focus now on elimination reactions, where we're taking something and we are eliminating. As opposed to substituting, we are eliminating. The removal of a smaller molecule from a larger one. Halogenoalkanes will lose a hydrogen halide and form an alkene. Use an ethanolic solution of sodium hydroxide, so sodium hydroxide in ethanol. So this sort of highlights why reaction conditions are very important in organic chemistry, because we want to be in control of the kind of products that we are getting. So we saw just before, if we get a sodium hydroxide in an aqueous solution, then we will end up with a substitution reaction to form the alcohol. But if we do the sodium hydroxide in an ethanol solution, then we will get an elimination reaction to get the alkene. For example, consider this reaction here, one that is mentioned in our learning outcomes. 2-bromopropane, elimination to get propene. Let me draw this up here in a displayed formula. So we have a 2-bromopropane, 1, 2, 3, bromine, like so. And then the hydroxyl in the ethanol, what's happening is, unlike in our substitution reaction where the hydroxyl was acting as a nucleophile and attacking that delta positive carbon, In this elimination reaction, rather the hydroxyl is acting as a base. Bronson Lowry base is a proton acceptor, and it's actually going in and it's plucking a hydrogen. It's accepting a hydrogen to form the water, which is what we get here. So the hydroxide is acting as a base instead of the nucleophile. So what this means is that this will take this hydrogen, and then this bond will form heterolytic fission to form a alkene, and then we will get the bromine leaving. So again, stressing the importance of the reaction conditions. The same reactant but different conditions will give two different products. So then we can get the bromine leaving and we form the alkene. So we're going to get a double bond there like that to get propene. Still got plenty of space here. And then we've formed water from the H2O, and then our bromide, which has left. Now, this can happen in either one step or two steps, depending on the type of halogenoalkane that we have. The bromine can leave first, and then we can get the double bond formed, or it can happen all in one step like that. Elimination reactions aren't ones that we're too concerned with the mechanism of, but we're going to see in the next lesson with substitution reactions how the one-step and the two-step processes for substitution reactions will differ in their mechanisms. Okay, so that's just a brief introduction into what the halogenalkanes are and some key reactions we need to be aware of. Halogenalkanes are interesting because they're not found all that often in just in nature. However, they have a huge number of uses in all sorts of industries. But then it was found that there was large environmental ramifications from the excess with which we were using them. So that's what we're going to have a look at now, the uses and the pollution of these types of compounds. A number of uses, including acting as refrigerants, solvents, flame retardants, refrigerants, double the refrigerants, propellants, also in the pharmaceutical industry. For example, halothane as an anesthetic, halothane being 2-bromo, 2-chloro, 1,1,1-trifluoroethane. Why don't you have a go at trying to draw that? See if you can work it out. It is a very substituted halogenalkane. So what have we got? If I find my pen. We got an ethane, 1, 2. We got 2-bromo, 2-chloro. So let's say bromo, 2-chloro, 1,1,1-trifluoro. F, F, F. Like that. So it is a very inert molecule due to very strong CF bonds, safe to use inside the body, and it can act as an anesthetic. So put you to sleep. Like I said, they're rarely found in nature, but very common intermediates in chemical synthesis on top of all these other uses. And they were initially thought to be these sort of wonder compounds that could do no wrong. They were very unreactive. They had a number of uses, very useful uses. But then it was later discovered that actually it was depleting the ozone layer, especially above Antarctica. The ozone layer, very, very important for protecting the Earth from harmful UV radiation from the sun. So the ozone molecules can absorb that UV radiation, and that means that it doesn't get down from the stratosphere into the Earth's surface, which, I mean, if we talk from the human side of it, UV radiations can be very harmful to us. So let's discuss that. So our chlorofluorocarbons, class of molecules containing CH, because they're they're alkanes, Cl and F, so chlorofluoro, a specific type of halogenalkanes. For example, dichloro-difluoromethane, common name of Freon 12. That would look something like this, dichloro-difluoro. So let's say we've got dichloro, difluoro. What do I need? Another straight line. Like that. If I show my sp3 hybridization. These are non-flammable, non-toxic, and inert. So you can see why they might be used as flame retardants, or why they might be used in anesthesia, or why they're used for a lot of these jobs because of these great characteristics that they have, these great properties that they have. So they frequently were used as propellants, solvents, and refrigerants. But like I say, it was discovered that there was a large hole in the ozone down below, or down above Antarctica, I should say, where the ozone was being depleted. So here's a little bit of a very short history of this.
First synthesized in the 1890s by a Belgian chemist, Frederick Schwarz. Improved in the 1920s. They were used extensively in World War II. Think about fire suppression, taking advantage of these non-flammable properties that they have. And then post-war, they became very, very commonly used for this whole myriad of uses that we found up here. And like I say, initially thought to be these wonder compounds, it was eventually discovered that they were absolutely destroying the ozone layer. However, heavy regulation in the 1970s occurred after discovering this destructive effect. And in 2007, around 200 countries agreed to eliminate CFCs entirely by 2020 at the UN Montreal Summit. And then just to show that, I mean, we talked a lot about the human destructive capabilities on the environment a fair few times in this course, actually. Pollutants of our oxides of nitrogen, our oxides of sulfur, our oxides of carbon and greenhouse gases. Here's another one, these CFCs and the destructive effect they had on the ozone layer. But with coordinated work between countries and agreed upon limitations to these things, there can actually be improvement. And that's what's been observed, is the ozone layer since they've been banned has been shown to repairing itself. So change can cause the environment to heal. We've just got to be able to organize that change. So yeah, to reiterate why the ozone layer is so important, in the stratosphere absorbs harmful UV light. It's a layer that protects the Earth. And whilst our CFCs are inert on the surface of the Earth, in the stratosphere, UV light breaks the CCl bond, forming a chlorine-free radical. Free radicals are something we looked at when we looked at our alkanes. Super, super reactive, well, I won't say atoms because they're not, they're free radicals. Super reactive species, and these can go on to have chain reactions that, decimated, depleted the ozone concentration. So by absorbing these UV lights, the ozone layer protects us. Specifically here in Australia, we have, we're down near the ozone hole, so we have a depleted ozone layer. So something like skin cancer is very, very prevalent here because we don't have that protection from this ozone layer. So very important to wear sunscreen. So what happens? So we get the conversion of ozone just into oxygen gas, which doesn't have the same ability to absorb the UV light. And then the chlorine-free radical is a catalyst, right? So we regenerate it at the end. So then this can go on to destroy another ozone molecule, and it will regenerate and go on to destroy another ozone molecule, etc., etc. And it's estimated that one chlorine-free radical can destroy about 1 million ozone molecules. So you can see how detrimental they can be, and our CFCs can remain in the stratosphere for approximately up to 100 years. But just to stress, people identified there was an issue with pollution, they rectified it, they regulated it, and we have seen the environment healing itself. Because the Earth and the environment is very robust. I mean, it is capable of self-healing if we allow it. So when we bring up a lot of these pollution things, they might seem very dire, and they are very dire, but there is always hope that the situation, if action is put in place, will be able to improve. That's it for our first lesson looking at the halogenoalkanes. What have we done? Recall the chemistry of halogenoalkanes is exemplified by the following nucleophilic substitution reactions of bromoethane, hydrolysis, formation of nitriles, formation of primary amines by reaction with ammonia, the elimination of hydrogen bromide from 2-bromopropane. Then we explain the uses of fluoroalkanes and fluorohalogenoalkanes in terms of their relative chemical inertness, recognize the concern about the effect of chlorofluoroalkanes on the ozone layer. Tasks for this lesson: pause, work through that, and you will help to solidify what we've covered in your brain. Excellent. Thank you for your time. I'll see you in the next lesson when we conclude our look into the halogen derivatives and our halogenoalkanes. Have a great day.